Hi everyone, welcome back to Chem Story. Today, we're going to take a look at how ethers are made. There are a few different ways to do it, and the method you choose really depends on what you're starting with. Sometimes you might begin with an alcohol, and other times with an alkyl halide. Some reactions are pretty simple and happen in one clean step, while others depend on the reaction mechanism, like whether it goes through SN1 or SN2. By the end of this lesson, you'll have a solid understanding of how to synthesize ethers in the lab. All right, let's jump in. All right, let's start with one of the most well-known ways to make ethers, the Williamson ether synthesis. In this method, we begin with an alcohol. Here, it's cyclohexanol, and we're going to turn it into an ether. First, we treat the alcohol with sodium hydride, or NaH, to remove the proton. That gives us an alkoxide ion, which is a strong nucleophile. Next, we add a methyl halide, like methyl iodide, and that sets up a classic SN2 reaction. The alkoxide attacks the methyl carbon, kicks out the iodide, and that gives us our ether. This reaction works best when the alkyl halide is primary. That makes the SN2 step clean and efficient. And the cool thing is, it's super versatile. You can make all kinds of ethers just by switching up the alcohol or the alkyl halide. Here's another way to make ethers. This time it uses two alcohol molecules and an acid catalyst. We call it the acid-catalyzed dehydration of alcohols. In this example, we're starting with N-propanol. When we add strong acid, like concentrated sulfuric acid, and apply heat, two N-propanol molecules react with each other. One acts as a nucleophile, and the other gets protonated and turns into a better leaving group. In the end, we get dipropyl ether, and water is formed as a byproduct. This method works well for making symmetrical ethers from small, simple alcohols. But it's not ideal for unsymmetrical ethers or for bulky alcohols. The reaction can get messy, and sometimes elimination takes over instead. Let's switch gears and look at a different approach, this time starting from alkyl halides. In this method, we react an alkyl halide with an alcohol. And here's the key part. The reaction mechanism depends on the structure of the alkyl halide. If it's a primary alkyl halide, like the one in the top example, the reaction follows an SN2 mechanism. The ethoxide ion attacks from the backside and kicks out the bromide. It's a clean, one-step process. But if the alkyl halide is tertiary, like in the bottom case, SN2 doesn't work because of all the steric hindrance. So instead, the reaction follows an SN1 pathway. First, the leaving group, Br- falls off, and that forms a carbocation ion. Then ethanol steps in as the nucleophile and attaches to the carbocation ion. In both cases, you get an ether in the end, but which path the reaction takes depends entirely on the structure of the alkyl halide. Now let's take a look at how we can make ethers starting from alkenes. One really useful method for this is called alkoxymercuration demercuration. Here's how it goes. We start with an alkene, like cyclohexene, and react it with mercuric acetate, using an alcohol as the solvent. In this example, we're using ethanol. The double bond reacts with the mercury reagent and forms a cyclic intermediate. Then ethanol, acting as a nucleophile, adds to the more substituted carbon, just like you'd expect from Markovnikov's rule. In the next step, we bring in sodium borohydride, NaBH4, to remove the mercury group. And in the end, we get an ether with the alcohol part now added across the original double bond. It's a clean, regioselective reaction and a really handy way to make ethers from alkenes. Here's another way to make an ether from an alkene, but this time we're using a halogen. When you treat an alkene with something like bromine, in the presence of an alcohol solvent, something pretty interesting happens. Let's break it down. We've got cyclohexene, and we're adding Br2 in ethanol. The double bond reacts with the bromine and forms a bromonium ion, just like in a typical halogen addition. But here's the twist. Instead of water, ethanol is the nucleophile because it's the solvent. So ethanol opens up the bromonium ring from the backside, and the product we get is a bromether, where the OET part from ethanol is now attached to the molecule. This is a perfect example of how the solvent itself can actually become part of the product. All right, now let's shift gears and talk about making epoxides, which are just cyclic ethers with a three-membered ring. The first method we'll look at is called epoxidation, and it uses something called a per-acid. One common choice is MCPBA, that's metachloroperoxybenzoic acid. But really, most paracids can do the job just fine. The alkene reacts with the paracid in a single step. The oxygen is transferred straight onto the double bond, and that forms the epoxide ring. And here's the cool part. It's a stereospecific reaction. That means whatever stereochemistry you had in the starting alkene gets carried over into the epoxide. It's simple, it's clean, and it's super useful when you're doing synthesis. There's one more common way to make epoxides, and that's by using a halohydrin in an intramolecular SN2 reaction. Here's how it works. We start with an alkene and react it with a halogen, like Cl2, in the presence of water. That gives us a halohydrin, which has both an OH group and a halogen on neighboring carbons. Next, we add a base, like NaOH. The base deprotonates the OH group, turning it into an alkoxide. And that alkoxide quickly swings around and attacks the adjacent carbon, kicking out the halide in a classic backside SN2 reaction. That's what closes the ring and forms the epoxide. This method takes 2 steps, but it's especially useful when you want control over the stereochemistry. And that brings us to the end of today's lesson on how to synthesize ethers and epoxides. We looked at a variety of methods, some starting from alcohols, others from alkenes, and saw how each one gives you a different type of ether depending on the conditions. Each method has its own strengths, so depending on your starting material and what you're trying to make, you've got plenty of options. Thanks for watching Chem Story, and as always, I'll see you in the next video.